Good morning. Let's get started. So this program, some average program, we have seen already. So here, just to recall, what do we do in this program? Uh, remember, this has two functions, max, average, and main, three functions actually. Main is anyway a compulsory function, and from main we are calling average, and we are calling max. On line 28, we are calling average, and on line 29, we are calling maximum. Uh, so, so the idea here is, if you see, so this is your main, and so let's say in the inputs that are supplied on line 26, let's say 10 and 20 are supplied as input in response to the scanf function on line 26. And first we are calling the average function. So we are calling the average function. If you see on line 28, we are calling the average function. We are calling the average function with 10, 20 as parameters to that function. And then after, so what happens is after the average function is called, average function gets executed, and then after that main calls the max function again with parameters 10, 20. So what happens is when main calls average, so control transfers here. So and then you kind of go like this. So main calls average, average gets executed, and then again you call max. So max gets executed again. You come back. And what I would like you to understand is we kept using this word stack. So generally speaking, so stack is a data structure which you will study later. You can think of stack as a kind of an array on which you can push items. So when you push, you can either push something onto the stack. So let's say you can say push 10 onto the stack. And when you pop something out from the stack, whatever that is there on the top of the stack gets popped out. Yeah, so exactly like a stack of plates. You can keep pushing one plate after another on the top of the stack, and then we can remove it. And then, so pop means whatever that is there on the top of the stack gets popped out. Like for example, here, let's say in the stack already elements 4 and 10 are present. This is a logical picture. This is a logical picture. So when you push 10, let's say you push 20 onto the stack. So when you push 20 onto the stack, then the stack looks like this. So 10 is present here, 4 is present here, and 20 is present here. This is how the state of the stack changes. And when you do a pop from the stack, whatever the element that is present on the top of the stack, it gets popped out. So here, so after this, when we apply a pop, then so this happens when you do push 20. So the state of the stack moves from here to here like this. And when you do a pop, then what happens is 20 gets popped out, and the state of the stack becomes like this again, 10, 4, and 20 get popped out. We are not doing, I'm just introducing stack for a reason. We are not doing any of the data structures. So what happens is, in order to execute, so in order to handle functions, there is an implicit program stack or call stack that gets maintained. You don't do it. It's not in your purview at all, but the compiler kind of sets up things in such a way so that this stack manipulation happens automatically. So for example, here, when you are in function main, so there will be some stack. So on the stack, so there will be some data items associated with the function main on the stack. This is what is called as a program stack or call stack. Or call stack. And when main calls average, what happens is the state of the stack moves from this to this. So there will be, so the call stack for this is what is called as the frame or activation frame or activation record associated with main. So we can, let's call this as activation record, activation record associated with main. And when average gets called, so then what happens is the activation record for the average function will be pushed onto the stack. So the variables, like for example, if you look at the activation record for the average, average has two variables A and B. They are parameters, but they are, for all practical purposes, they are just like local variables. The memory for the local variables A, like for example, the memory for A and B will be allocated on the activation record associated with the average function. And then, so after when we come out of this average, then what happens is the state of the stack comes back to this. Okay, because the activation record associated with average will be popped out, and the activation record that is present on the top of the stack is main. And then, so when main calls max, then what happens is the state of the stack becomes something like this. So this is the activation record for main, and this is the activation record for max. And again, if you see, max has two local variables A and B. They are allocated memory here, A and B. And if you look at main, main also has two local variables, capital A and capital B. The memory for A and B is allocated on the stack. I wanted to bring this up because when you look at this picture, it becomes clear why the lifetime of the variables A and B in the average function or in the max function, it is only when that function is active, because as soon as the function is returns, that is the execution of the function finishes, the associated activation record gets released. So the memory that is allocated to the local variables is no longer available. Capital A and capital B, they are variables on line 22. Yeah, when a function returns a value, it gets popped off from the call stack. Yes, that's true. When you call a function, the activation record will be pushed, the function executes, and after the function finishes execution, the activation record gets popped out. That's what happens. So yeah, if there are more local variables, then correspondingly the size of the activation record will be larger. I think you are all there. I'm seeing lots of questions which are, if you recall the discussion from the last class, let me erase this part and activation record is there for every function that is activated. This idea is very important to understand so that when you, so remember what is the main memory layout for a program, logically speaking. So for the sake of simplicity, so remember there is this kernel. So this is the memory layout for a program. This is for the operating system kernel. And then there is a stack here. This, and then there is code section here. And then there is data section here. And then there is malloc heap. And stack grows in this direction and heap grows in this direction. Are you fine with this picture? Do you recall this picture? This is the logical main memory map of the program. So the instructions associated with the program the instructions associated with every function, they are present in the code section. And the memory for the local variables, it is allocated in the stack. And if you take a kind of more finer look, the memory is allocated in this logical structure called as an activation record associated with that particular function activation. And the memory for global variables is allocated in the data section. Are you with me on this one? There are a few questions. I just want to see how many of you are with me. And if you have any questions, I can answer them now.
So what is the exact definition of activation record?
Last year. So there is no this is understand activation record from a functional perspective. Associated with every function, in order to carry out the execution of a function, we need in order to carry out the execution of a function, we need some paraphernalia. So one of the important things is the memory for the local variables. So the memory for the local variables and parameters, etc., it will be allocated in the activation record associated with a function. And it is dynamic in nature because let's say when we are in main, the activation record for average or max is not there. Only when you call the average function, what happens is the activation record for average will be pushed onto the stack. It will be created here. And then when you come out of the average function, that is when you return from the average function after the execution, the activation record associated with average will be deallocated. That's true. So the activation record is just the stack of allocated memory for the current function in use, for the current function which is there on the top. The data for the local variables, it is present in the on the stack. If you're all with me, I will proceed to the next idea. Can I proceed? Are you good? Okay. No, so see what I will explain, Anish. I will answer your question in a moment, actually. So I'm clearing this annotation and moving to the next program. I will answer some of the questions that you have by considering a different program. So this is our first twist with what is called as recursive functions. So here we are trying to compute factorial. So when you compute, so what is factorial function? So the way we can define factorial, so you know factorial n is equal to, so 1 into 2 into 3 into so on up to n. This is how it is defined. But there is an alternate way to define factorial. So we can say fact of n is equal to, so there are two possibilities. It is equal to 1 if n is equal to 1. Otherwise, it is equal to n times fact of n minus 1. So that's it. So this is, if you think about it, so so what is let's say if it is fact of 2, then fact of 2 is nothing but 2 times fact of 1, but fact of 1 is nothing but 1, so it is equal to 2. So this is a recursive function. Yeah, it calls itself. So similarly, if you see, so fact of 3, so fact of 3 is nothing but 3 times fact of 2, and so but the fact of 2 is nothing but 2 times factor of 1, and so this goes to 3 times 2 times 1. So this is equal to 6. So here, so we can use these recursive definitions, which are if n is equal to 0 case, yeah. So if n is equal to 0, then again, yeah, we can handle that case also. We can add that. Yes, I'm not being precise. Yeah. So, so that is how you can see. And we did, and if you look at the code here, and that's what exactly being done here. So you say factor of n, so factorial 4, let's just compile this program and execute it, and we'll see. So gcc fact.c ./v.out, factorial 4 is equal to 24. So here what is happening is, if you see, when we call factor 4 on line 7, what happens is we check if n is equal to 4. So let's see what happens. So the time complexity of this algorithm is linear, so we will come to that later. Okay, so maybe it's a linear time algorithm. Okay, for the time being, we can just think of it as that. So let's say in this particular case, we are calling factor 4, and when we call factor 4, what happens is on line 7, we check if n is equal to 1, n is not equal to 1, so you go to line 10. And on line 10, what you do is you say 4 times factor of 3, you call factor of 3. Okay, and then when factor of 3, we go back here, we check if n is equal to 3. If it's not the case, so you go to again line 10, and this is what happens. So now let's try to debug, let's try to run this program in a debug mode and see what happens. So please pay attention here. This is the important thing, okay? So main call, I want you to pay attention to call stack. I want you to, so I want now the chat to stay focused here for some time so that everyone understands. So if you see the call stack, main called fact. So that means if you look at and the value of n is equal to 4. So if you look at the activation records that are there on the call stack, so the activation record, so this is main, and then there is an activation record for fact with parameter 4. You can see the value of n is equal to 4. And n is allocated, n and variable factorial, they are allocated memory in the activation record associated here. Okay, let me draw it clearly. So let's say this is, I'll start close here. So this is the activation record associated with, so this is for main, and this is for fact with parameter 4. And if you see, memory will be allocated for 2 variables. One is for n, the other is for factorial. And you can see the value of factorial, if you see, it is some garbage value. It is a local variable. So at this point, when we are on line 7, the value of factorial, it is some garbage value. All right. When you say procedure, does it mean no, C frame? So in some old programming languages, people use the name procedure for functions which don't return any value. And instruction set is completely different from procedure. Uh, are you all with me here? That y factorial is not, it has some garbage value, and the value of n is equal to 4. Okay. So now let's step through the code. Now we are on line 11. If I press function key F11, we check n is equal to 1, and n is equal to 1, it's false. So we come to line 10, and on line 10, so now you can see, if you check the call stack, so fact of 4 called fact of 3 again. So what happens here is, if you look at the activation record, so this is the activation record for fact of 4. So this is the most important idea, that there are multiple activations of the same function uh, at the same time, which are active at the same time. And the memory for the local variable n, for in fact, sorry, this is fact 3. The memory for the local variable uh, n and factorial, so factorial will be different. So this n is different from this n. This n is different from this n. This is very, very important. There are two different versions of n at this point in time. One n is associated with fact 3 and another n is associated with fact 4. So now if you want to go and see what is the n associated with fact 4, you click this one, and now we are in this particular activation record. We are able to do it using GDB, and you can see the value of n is equal to 4. Are you with me here? Like, why when we go and take a peek into the activation record associated with fact 4, the value of n is equal to 4. And when I click here, now we have moved to the activation record associated with fact. That's true. For every time you call a function, the associated activation record will be created. So now what happens is, if you step through the code, so now what happens is, we are, so now fact, if I see write the code here, so this is the activation record associated with fact 2. And so again, you can see there is an n and there is a factorial. So there is memory for factorial variable allocated. And now let's see, let's step through the code again. Uh, so now fact 2 again calls fact 1. So now if you see the call stack, so this is fact 4, this is fact 4, this is fact 3, this is fact 2, this is fact 1, and uh, so, and this is fact 1, and then what happens is, and when we are in fact 1, what happens is n is equal to 1, and if you step through the code, so here if I draw the picture here, if I continue to draw the picture here, this is fact 1. And each of them, they have their own versions of the variables. Each of them, they have their own versions of the variables. And the value of the, very good observation, Radhesham. So the value of factorial until this point in all the activation records, it is a garbage value. It just so happened to be 0 in this case, but we don't have any assurance of that. So now what happens is, when n is equal to 1, so now when I step through the code, so this becomes, we come to return 1, and so this activation record associated with fact 1, it gets popped out. It gets popped out. So now you do, now we come to fact 2. What is there on the top of the stack? Yeah, so now this, we are in fact 2. Well, there is a particular thing. So what happened is when we, I don't know whether, what's, see what happened is in fact 1, n is equal to 1. So we are saying return 1. Okay. So we are doing return 1. And when we return 1, what is the status? The activation record associated with fact 1 will be popped out. And what we have is fact 4, fact 3, fact 2, and main. This is main. This is fact 4. This is fact 3. And this is fact 2. And now in fact 2, you can see the value associated with the factorial variable is equal to 2. The value associated with factorial is equal to 2. And that's what gets returned to the fact 3 call. That's what gets returned to the fact 3 call. So we come back again. So you can see the top of the stack is fact 3. So fact 2 got erased. Okay, so let me draw this. So from here, we have come here. So this is fact 3, fact 4, and main. Are you with me on how this whole thing is unfolding? And then again, you come back, so you come out. So that's all. So you keep going like that. So the activation records, they keep getting popped out. So finally, we, yeah. So we tried to do a kind of stepping to printf. So, but anyway, so leave that aside. Are you all with me on this one? What is happening in this code? So how the activation records kept, we keep calling function, 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 and then we keep unwinding them. We define 20 factorial, we check if n is greater than 20, then yeah, fact 1 returns 1, fact 2 returns 2, so on and so forth. So if I, let me draw a different picture for you so that you get a clear understanding. So here, this is the picture. This is the different picture I would like you to keep in mind. So main calls fact 4. Fact 4 calls fact 3. Fact 3 calls fact 2. And fact 2 calls fact 1. And fact 1, it returns, I am using a different color. So fact 1 returns 1, the value 1 to fact 2 from line number 8. From line number 8. And what fact 2 will do is, it will use that value 1 here, and it will have 2 times 1. 2 times 1 is 2. So it returns that. It returns 2 here. So, and then what happens is, if you see fact 3, so fact 3, if you look at fact 3, so fact 3 says 3 times fact 2, but fact 2 is nothing but 2. So 3 times 2 is 6, it returns 6. And then if you see fact 4, so if you see fact 4, what happens in fact 4? Yeah, if you think in fact 4, it calls 4 times fact 3, right? But fact 3 has returned 6. So 4 times 6 is 24. So it returns 24 to the main. Do you see how these values are getting propagated back and how the whole thing is working? Great. So if you understand this example, then it's fantastic. So it's in the sense you really know a lot about programming, and this takes you uh, a long way. Uh, yeah, that's true. The stack gets popped off as the values are written. So there are a couple of interesting questions on time complexity. If you look at the time complexity, in this particular case, the space complexity and time complexity, let's say without, we can loosely say the time complexity is n because the depth of the recursion is n, the depth of the stack is n, and the space complexity is also n, the depth of the stack is n. But let's say if you're not happy with this, with this space complexity of with depth n, then what can we do? We can write this code in the form of a loop. Let's see, we can kind of do this thing. So main, so control S. So int fact, I'm not even using a, or let me do this thing. Yeah, let me go to this, control C. So here, what I can do is, so int factorial is equal to 1 for I is equal to 1, I less than or equal to n plus I factorial star n. Is this code correct? Okay, in type. Okay. So let's compile this code. Okay. So one subtle observation here is the space complexity in this case is constant because we are using only one variable factorial. There is a bit of an issue, but for the sake of simplicity, when we compare this loop program with the previous recursive code, in the recursive code, we are maintaining this stack, and that stack costs us some space. It has linear space complexity, whereas this function, this particular code, where we are using the loop is, it's a, it has constant space complexity. So what is the issue as she's asking? So the issue is we will see later because what happens is when you try to compute the value of factorial, the number of bits explodes. So all this kind of thing, the complexity arguments that we are making, it kind of works if the value fits into, let's say, one word or one long word, or one int or one int variable or long int variable. But if it goes beyond that, then we have to consider some other things will kick in. So for the time being, we shelve those issues, and subject to that, we can simply say the loop has constant space complexity and linear time complexity, and whereas the recursive function has linear time complexity and linear space complexity. So I'll just write it down for your case. So we have seen two programs, two approaches for complexity computation, for factorial computation. So there are two approaches. One is using a loop, one is using a recursive function. So time complexity. So time is linear in both the cases. And if you look at space, this is constant. This is linear. I do not understand the advantage of. Yeah, good question, Vivek. Some no, factorial is a very trivial problem. You can write a loop, uh, but there will be some functions, some programs where it will be hard for you. It's easy for you to think recursively rather than to think in terms of loop. And it is not always the case that that loops are better than recursive functions. It depends. Yeah. So Pratyaksh has this very nice example about towers of Hanoi problem, or even the GCD algorithm that you may have computed in one of the homeworks, Euler's algorithm for GCD. So if you write a recursive there also, it is easy to actually to write loop code easily. But towers of Hanoi, you may want to check that thing. So uh, where recursion really helps. That's true. It can be less than n. So it does. Don't think this is the analysis that we did. It's for this program, and depending upon the algorithm, no, it kind of changes. Okay, depending. I just wanted to make a point here, and but depending upon the context, it many things will change. Okay, if you're all with me, shall I proceed further? There are a couple of more important ideas that I want to introduce. Shall I keep going? Good. Yeah. So this is about, yeah. So let's take this function. Uh, so take a look at this program. This is a very extremely simple program with one function, two functions. One is a count function. The other is a main function. You can see that the count function has a local variable counter. It is initialized to 0. And there is a qualifier called as a static. So what happens is, and let's run this program and see what will be the output of this program. So gcc static.c. So you can see the value of counter is 1 to 10. So this is very interesting because the value of the counter variable, when you call it for the first time, when you call it, it will be equal to 0. And then, so it gets incremented by 1 and 1 gets returned. So the value of the counter variable is retained across function activations. So the static keyword that we are using here, it tells the compiler to retain the value of this variable across the function activations. So if you see the way this kind of works, so main is there. So main called count for the first time, and count returned 1. And then again main calls count for the second time and count returns 2. And main calls count for the third time and it again returns 3. So on and so forth. If count was, that's true. If count is recursive call, the if count is a recursive call, the value of counter is available across all function activations. So there are two important ideas here. The first question is, what is the scope of the variable counter that is declared on line 5? Question, this is the first question. What is the scope of the variable counter that is declared on the line 5? The scope of the variable counter is only within this function. You cannot use the variable counter in the function main. It is only in the count function only. That's number one. What is the lifetime of the variable counter? So this is the scope of the variable. This is the scope. This is the scope of the variable counter. What is the lifetime of the variable counter? The lifetime of the variable counter is the whole program execution time. The whole program execution time. So how is it possible? So counter cannot be executed. So counter cannot be allocated memory on the stack, because as soon as count, we return from the count, the memory that is allocated for local variables is popped out. So counter cannot be allocated memory on the stack. So what happens is, you recall the discussion again. If you look at the program layout, there is a code, there is a OS, and there is a stack. You cannot allocate memory for counter on the stack, but then there is a data section here, and there is a heap here. So counter will be allocated memory in the data section. Counter will be allocated memory in the data section. Line 5 is only executed once, the very first time. It's not like that, Pratyaksh. Actually, it is kind of set up in such a way. In the data section, compiler tells, this is the variable, allocate memory for the variable counter and initialize it to 0. That kind of information will be entered here. Let's say if it is equal to 5, in the a dot out, the compiler kinds of sets up things in such a way that allocate memory for counter in the data section and initialize it to 5 when the program is being loaded. So there will be no code executed, actually, technically speaking, to do the initialization on line 5. So the counter gets initialized as soon as the program gets loaded into the memory. As soon as the program gets so why is yeah, so I will explain that, Abhinav. So there is this question. So there are two kinds of explanation here. Uh, okay, let me take, there are few multiple interesting questions. I will take a step back and I'll try to answer all the questions. So let's, so number one, the scope of the variable counter is restricted to the function count. And who enforces that restriction? Compiler. That's what Kishore answered in the chat box. Perfect answer, Kishore. So the accessibility is restricted by the compiler only. So when you use counter in main, compiler complains that, you know what, counter is not within your scope, so you are not allowed to use it. Are you with me on this one? Okay, are you with me on this one? I hope all of you are with me on this one. That compiler does not permit you. It's like compiler is like a schoolmaster or a school principal, which tells us this area is not yours, kind of thing. Okay, so that's number one. So scope is enforced by compiler. Let me write this one. Scope is enforced by compiler. All right. Number two, lifetime. The variable counter, it is available across program, this function activations. And line number 5, it doesn't result in any code. It doesn't result in any assembly instructions. It is telling the compiler, when you create memory for the counter, initialize it with initialize it with 0, or it can be, instead of 0, it can be any value. Like for example, it might as well be 5. So what happens is, the compiler, when it generates the a dot out, let's say this is your a dot out. In your a dot out, the compiler somewhere stores this information that counter should be initialized to 5, and it should be allocated memory in the data section. This information will be provided by the compiler in the a.out. And when you give your program for execution, a main memory layout for your program will be created. In the main memory layout, remember there is something called as a data section. And when this main memory layout, and there is a code section here, and when this main memory layout is created, the memory for counter will be allocated somewhere here, and it will be initialized at the time of program loading. At the time of program loading. Are you with me on this one? Are you all with me on this one? That this initialization of counter to 5 happens at the time when the program is loaded into the memory. So no code gets executed. So this is an important observation I want you to keep in mind. That's all. These are the only two things that you need to remember. And the lifetime of the variable counter is the whole program execution time, because that whatever that is allocated in the data section, it will be there. Unlike if something there is there in the stack, it will be allocated, deallocated depending upon whether the function is active or not, things like that. Any memory that is allocated in the data section, it remains there throughout the program execution time. The role of static tells us to do all these things. So static extends the lifetime of the function counter across program activations. If you don't use static is just a local variable which gets allocated memory on the stack, and when the function uh, is active, uh, memory will be allocated. When we return from the function, memory is deallocated. But by putting static there, counter is allocated memory here. So when you call count again, the previous value of the counter is still there in the counter. If you write the counter plus 1 before, it's not possible here because you need to have the declaration. You cannot have counter plus 1. Lifetime, if you don't use the static, lifetime would be restricted to when the count function is active. Scope, how is scope the whole function? Scope is restricted to only count. Okay, let me do one thing. So let's say if there is some other local variable, int blah. So what's the difference between blah and counter? The lifetime of blah is, yeah, it is only when the function is active. Oh, blah is not in the heap. No, 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 no. Blah is on the stack, and the counter is on the data section. Yeah. So what happens is when main calls, count, so this is the activation record for main, and when we call count, so this is sorry. So this is main, and this is count. This is the activation record for count. And if you look for activation record for count, only memory for blah will be allocated, because the memory for counter, it will be allocated in the data section. Okay, guys, are you with me? I thought I'm trying to explain in multiple ways. I'm also desperate to see that you understand the idea, but uh, let's see. Rajesh has a question. Okay, Rajesh, go ahead and ask.
Um, so Onru just said that he doesn't understand why the counter is not reinitialized to 5 every time the function is called. So the same doubt. Um, so like in Python, in Python and all, we have to use the global keyword. You were speaking about scope earlier, right? In Python and all, we have to use the global keyword so that if it's within the function, it gets updated outside the function as well. So like, how does that happen in C?
I exactly don't know the context of Python, so I have to review the semantics there. See, you should try to understand the semantics. There are two things I want you to appreciate here. Number one is what is the semantics defined by the language? Number two is how is it being implemented? Are you with me? These are two different questions.
Yes, sir.
Okay. The
So
semantics of this is when we have this something on line 5, that is when we start this program for execution, the value of counter will be equal to 5. The value of the counter will be equal to 5. That is a semantics. And later on, so the code on line 5, so it's just a variable declaration. We are just telling two things, that this variable is a local variable, and it's a static local variable, and it should be initialized to 5 when the program starts execution. That's what line 5 means. That's all it serves the purpose. When you call count again and again and again, line 5 doesn't have any impact on the execution of the count function.
okay, sir.
And how this whole thing works is the way I said. So the compiler puts in a dot out that there is a variable called as counter, and counter should be allocated memory in the data section, and it should be initialized to 5 when the program is being loaded for execution.
So suppose there's a variable, say count only, if it's declared outside a function, and then it's also within an if it and that variable is used within a function. So
Okay,
after
which
the
function?
so any random function, sir.
Okay, no
Just
problem.
any function, for example, and after the invocation and the how after the function is being done, if it's done being used, so will the value of the variable which was declared outside the function be updated?
No, no, no. So that counter and this counter, they are different. They will be,
Okay, sir.
you may just look at their names as the same, but that counter and this, like for example, you can have another variable counter in main, right? So these two counters are completely different from each other, so it wouldn't be an issue.
Okay, sir. Thank you.
Yeah, so Frame gave a good explanation. Static variables are initialized only once. If you come back to line 5, compiler already knows that it's initialized and is hence skipped. Okay, that's the best. If the initialization happens during compile time, is there no equivalent of line 5? No, I explained it. So what happens is in the a.out file, there will be information. So if you look at a.out file, somewhere in the a.out file, so actually we have seen there will be something called as dot data section. In that dot data section, something like this will be there. Counter, define word, 5, something like that will be there. So when a main memory map of the program gets executed from a.out, the memory for counter will be allocated in the data section, and that will be initialized to 5. And that happens at the time of loading the program from a dot out to main memory. And that is done only once. That's all. Are you with me on this one? Are you all with me on this one? Okay. So now I'll show one more program and then we will take a break for today's lectures. Every day I come to see that I will start with pointers, but it's not happening. But it's all right. So now let's look at LCG code. So this is the LCG code. So here, let's say this is what I'm going to do. Static, okay, this is going to be an issue. Okay, I think I'll hold this example because I see there is a problem. I wanted to modify LCG code in a particular way, but I'll stop that exercise because I see one problem there. Okay, then. I think I should, time now is 11:30. I don't want to start a new topic. So I should stop here. But I hope you're all with me on this, on the ideas discussed in today's class. Uh, so yeah, so that's all I have for today. So